series on complex analysis for undergraduate students. Today's lecture is on Cauchy's integral theorem. We have learned about the contour integrations, that is the integration of complex function in complex domain. Till now what we have done the contour integrations, we had find out that for some functions the integral depends on the contour, while for some functions integral does not depend on the contour. In the case when it is not depending on the path, we can use the indefinite integral of the function, and then we can use the limits for that from z0 to z1 what is the true points, and we can calculate the integral independent of any path. Now, today we would let us find out the reason why for some functions the integral depends on path and for some function it does not depend. So, let us first see, suppose that p x y and q x y are two real valued functions which are continuous with their first order partial derivatives are also continuous in some closed region R, which contains points interior to and on a simple closed contour C. Then according to the Green's theorem in advanced calculus, we do know that about line integral, that integral along the contour C of p dx plus q dy is same as the integral over the region of q x minus p I with respect to dx dy. Let us see that is what it is saying. This is the region x y. So, this is x y domain, or that is a Cartesian plane, or you could say is the z plane. Here is some region R which is enclosed by a contour C. This is the contour C. We have taken this contour in positive orientation, that is in anti-clockwise, so that every point which is interior to this C is left to this one. So, we are saying is that the integral along this contour of two functions p and q, p with respect to x and q with respect to y, is same as that double integral in this complete region of q x is the partial derivative of q with respect to x, while p y is the partial derivative of p with respect to y with respect to both the variables x and y, that is this region double integral. Now, let us use this result in our complex functions. So, we have started with the complex function f z, which we could say is that u x y plus I v x y, that we could write. We had seen in the contour integration, that is integral f z d z, in the last lectures we have done it, can be given as integral c u dx minus v dy plus I times integral over c v dx plus u dy. When we have presented our function f z as u x y plus I v x y, and we said z is x plus I y, and the contour C can be presented on that line, on that contour C, the z we are giving in the parametric form. Then we have done in the last lecture this formula. Now, in this formula we could apply the Green's theorem. Why? We are assuming is that function f is analytic. F is analytic, that means f is continuous. If f is continuous, then certainly u and v would also be continuous, and its derivative if is continuous analytic, that means u and v. If f dash is continuous, then u dash and v dash with respect to partial derivatives with respect to x and y, they would also be continuous. So, now we would apply the Green's theorem in this result. What it says is, if you do remember, the Green's theorem says is the line integral along the contour u dx plus q p dx plus q dy we have done is q x minus p y, that is its partial derivative with respect to x and its partial derivative with respect to y, and this would have with the minus sign. So, now we could write it out, this one, this would be minus u y minus v x dx dy. Similarly, this could be given as its partial derivative with respect to y and its partial derivative with respect to x. So, u x minus v y dx dy. So, what we have got, the integral in the region R, where this contour C is enclosing this region R, that integral of minus u x minus u y minus v x and of u x minus v y. This integrand minus uy minus vx, and this integrand ux minus vy, both are 0. Why? Because f is continuous analytic. So, Cauchy-Riemann equation says ux is vy and uy is equal to minus vx. So, ux is equal to vy and uy is minus vx. This gives both integrands to be 0, and it is a closed region R. So, the integrand, when both the integrands are 0, this would give 0. So, what we have got actually, that now if here I have taken the orientation as the positive one, that is counterclockwise, but actually this orientation does not matter because we have got this integral to be 0. So, if the orientation has been reversed, then we do know that integral c f z dz can be given as is same as minus of minus c f z dz. Minus c means that is orientation has been changed to the reverse to this one. So, this is minus of this one because this is 0. So, this will also be 0. That says is orientation is not matching what we have got now. Let us state the result which we have got from here. We have got the result, if a function f is analytic at all points interior to and on a simple closed contour C, then integral C f z dz is 0. That is, for any analytic function, we do get that for the closed contour, simple closed contour, integral of f z dz would be 0. So, we could verify it. The proof is as such, we have actually find it out, that is the proof. You can go ahead with this. F z is analytic, we write it f as ux plus I v y, and write this contour integral using that formula, and this just in the last slide what we have done, that we could call the proof of this theorem. Actually, this theorem has been given by Cauchy, and the proof has also been given. There we had used the continuity of the f dash. Next, this Gosset has done it, that is without using the continuity of f dash. He has given more general result, which said is that only f is analytic, and he had also shown that f dash is also analytic. Actually, any derivative of f would be analytic in this region, that we will do later on. So, here we just first verify this result for our examples. You do remember in contour integral we have done one function z square. Z square we do know is an entire function, that is it is analytic everywhere. So, and f dash z is 2z, which is continuous everywhere. So, all these conditions are being satisfied. That says if I do take any closed contour, simple closed contour, I must get integral to be 0. Now, if you remember in the last lectures we have done one example where we have taken the integral of z square from the point 0 to 1 plus I. If you do remember, we have done this example using different contours. One we have done is using this line, straight line from 0 to 1 plus I. Another we had used is using the 0 to 1 and then 1 to 1 plus I. And we had got that in each case our integral has come up same. So, now you see I am making this a closed contour. This C is now my closed contour from 0 to 1 plus I, then to 1 and then to this one. Now, since the integral along this line as well as this plus this line, they were same. So, if I am changing this direction for these two integrals, whatever integral we have got over here, that would be negative of that one, and that gives, that is in this direction it should be 0, and that we had verified it. Actually, we had find out in the last example that it is coming out to be same. So, the sum of both these integrals would be 0, and this theorem also says if I take any closed contour. So, this is the example because we have done in the last lecture. So, I have taken, actually you can take any closed contour, you can take any circle, any ellipse or any closed contour. This will always give you the integral as 0 because of this theorem, since z square is an entire function. Now, let us move to the general results which we are calling as the Cauchy's theorem. How do we find it out that when we could say it would happen? So, let us move to some more results. One definition, we are defining connected domains. Connected sets we mean is, that is the set which cannot be partitioned further with limits not being common to all. So, we are not very much interested in connected set definition as such if you are not remembering or if you have not done that over there. Here we will define it simply in two manners. One we would call simply connected domain and another we would call multiply connected domain. What is simply connected domain? A simply connected domain D is such that every simple closed contour within it encloses only points of D. What it is saying is, if I take any simple closed contour, its interior points are only points of D. Let us see some examples here. This is our domain D. If I take here any closed contour, simple closed contour, suppose this closed contour I have taken. Now, you see the interior points are only the interior points of this domain D. Now, suppose if I shift this contour to little bit this side, then it will become outside this one. So, this will not be inside the domain D. If I take any contour in this domain D, it will always take the interior points would be only the interior points of D. Now, you see another example. Here is a domain. If I take any closed contour in over here, you can just check with yourself also. This is also a simply connected domain. Similarly, you see this is also a simply connected domain, because if I take any contour over here which is inside this domain D, that will contain only the points of D. Certainly, disk is not a simply connected one. See, this is also an example of connected, simply connected domain. Here is also example. So, any closed bounded circle or ellipse or this would be your simply connected domains. This is also a simply connected domain. This is also a simply connected domain. This is also a simply connected domain. Now, if a domain, what is multiply connected domain? So, multiply connected domain, the domain which is not simply connected is called multiply connected. We had seen that is in the last examples, all the bounded domains we have taken about for the simply connected domain. So, if we are talking about all the bounded domains, in that case what the multiply connected domain could be, we could actually rewrite this definition. If bounded domain D is called P fold connected, similarly we call simply connected as 1 connected and multiply connected as P connected also, if its boundary consists of P close connected sets without common points. In the last example I said is that disk is not a simply connected. You see what is the disk? This disk is having the points, we are having this complete disk as the domain. The points which are interior to this inside inner circle, they are not in the domain D. So, now if I take a closed contour over here, say let us say this circle, then the interior points are the points which are not in D. So, of course, it is not a simply connected domain, but we can call it doubly connected or two connected. Why? Because you see in this domain we do have two boundaries. One is this outer boundary and another is this inner boundary. The points on this boundaries are these points and points on this boundaries are this. So, the set of these points on the two boundaries, they are disjoint. So, we do have this domain has two disjoint boundaries, that is domain, the boundary consists of two sets which are disjoint. So, it is doubly connected. Similarly, you see this is a triply connected domain. Why? We do have here one boundary, this is outer boundary, another is this inner boundary and then third one is this inner boundary. Certainly, this is not a simply connected, because if I do take a contour just like this kind of circle. So, this contour is completely inside the domain, but its interior does not contain all the points which are interior points of the domain. So, this is a triply connected because the boundary consists of three boundaries and each boundary is disjoint to each other. So, we do have this triply connected. Similarly, this is you see is that is we are having the 1, 2, 3, 4 and 5 boundaries. So, we will call it 5 connected, this is one outer boundary, 2, 3 and 4. So, we will have this 4 connected. What we have got? One more simple conclusion from here. If it is a bounded domain, we will call it P connected if it has P minus 1 holes. So, it is doubly connected 1 hole, triply connected 2 holes, 4 connected 3 holes, 5 connected 4 holes. So, if it is having P minus 1 holes, then it will call it P connected. So, this is the definition of multiply connected domain. Now, in the reference of this simply connected domain, let us see, we have defined the Cauchy theorem, which says is that for a simple closed contour, the integral will always be, integral of an analytic function will be 0. So, now rewrite this theorem in simply connected domain, we will call it Cauchy integral theorem. If a function f is analytic in a simply connected domain, then for every simple closed contour C in D, integral along that closed contour C of f z is 0. Now, we have not taken any other condition, that is whether f dash is continuous or anything. We are just taking is that it is lying in the simply connected domain. Now, so this is simple contour. Now, if it is not, this theorem can be extended to any closed contour rather than simple closed contour. Simple closed contour means is that is it is not intersecting itself at any point. If I do have any contour, that is it is not a simple closed contour, C in D can be replaced by any closed contour. So, suppose this is a closed contour which is intersecting itself at a finite number of times, even then this theorem would hold, or this result of this theorem, that is integral along this closed contour C of f z would be 0 if this contour is lying inside a simply connected domain. Why we could do is, if it is lying inside the simply connected domain, say for example, if I am talking about this contour, this closed contour I can break into 3 parts. One is this closed contour, another is this closed contour, and then another is this closed contour. For each closed contour, this is a simple closed contour. For each simple closed contour, this Cauchy theorem will hold true. That says is if I add up all these 3, I would get the final integral as 0, and then we would say is that any closed contour it would be 0. So, here the Cauchy theorem is actually about the simple closed contour, but we can extend this result to any closed contour in this manner. Let us see that is what it is actually referring to. We are actually basically interested in finding it out in what sense we could say that for a function the integral will depend upon the path, and for what functions the integral does not depend on the path. So, now we are talking about analytic functions. We had find out if it is on any simple closed contour, the integral along that contour will always be 0 for analytic function f. This says is that our independence of path. So, I am writing that result in form of theorem. If a function f is analytic in a simply connected domain D, then integral of f z is independent of path in D. Let us say z1 and z2 be any 2 points in a simply connected domain D. So, let us see, this is my simply connected domain D, z1 and z2, these are any 2 points. Now, I want to say is that integral of f is analytic in this whole domain. I want to say that integral along this integral of f from the point z1 to z2 would be same whether I reach in this manner or I reach from this manner or I go with any other path, it should be independent of path. See, what we are saying is, I would use this Cauchy integral theorem. This is a simply connected domain. I had made one simple closed contour passing through these 2 points z1 and z2. I have taken it positively oriented. Then according to this Cauchy integral theorem, I do have that integral f z d z is now this closed integral, this closed contour, the integral should be 0. Now, this closed contour I am dividing into two parts. One is from z1 to z2, this c1, and another is from z2 to z1 as c2. So, I could write it as c1 f z d z plus c2 f z d z, that we do know by simple definition of our integrals. We could write it out, that is the path we can write as the summation of these paths. So, this is equal to 0 according to the theorem. Now, what it says is from here integral c1 f z d z should be minus of integral c2 f z d z. Now, if I take the sense reversal property, then minus of integral along c2, that could be given as integral along minus c2. So, what we do get integral from on the path c1 is same as integral on the path minus of the integral on the path c2, which is same as integral on the path minus c2. That says is whether I am using this path or I am using this path, this would be same. Now, here I have taken this closed contour. Actually, we can make infinite many closed contours passing through these 2 points, and for each path I would get it like this one. Now, here I have taken the simple closed contour. So, my paths are not intersecting each other. Now, if suppose the path from z1 to z2, I do talk about the two paths such that they are intersecting each other. So, see what we could say is, suppose these are the 2 points z1 and z2, and we do have that the one path is this red path and another path is this green dashed path. These paths are intersecting each other at a number of points. Now, here for example, I have taken that they are intersecting at 3 points. We want to say even if this is happening, still the integral of an analytic function from z1 to z2 will remain independent of path. So, we are taking it that it is intersecting at 3 points A, B and C. So, crosses each other at many points. Now, what we will do is, as I said, is that is the Cauchy theorem is holding true even if I do take the path not simple contours, but the contours with any contour. So, here I am taking this as any contour, rather we will just use this Cauchy theorem for different segments. So, let us say first this from z1 to A, this is a closed contour, and for this the Cauchy theorem holds true, that is along this path of this closed contour, this integral will be integral of analytic function f would be 0. Similarly, along this path from A to B, this contour closed contour, then from B to C this closed contour, and then from C to Z to this closed contour. Now, so I am writing this complete contour, that is complete with the red and the green from containing both Z1 and Z2, this complete contour. This I can break into 4 contours. This first contour from Z1 to A we are calling C1, the second contour from Z2 to B, in this again I am taking all the positively oriented, that is the inside points, interior points are on the left of this one, and then this is from B to C, this contour when we are talking about this closed contour C3, and this is closed contour C4. Now, you see, so all these 4 are the simple closed contours in a simply connected domain. So, integral along this of any analytic function along these closed contours would be 0, that says this final integral would be 0. Now, I am writing this first integral, that is first this simple closed contour. First I will take this red path from Z1 to A, this is C11, and then this green path from A to back to Z1 in this direction, this is C12. Similarly, for C2 I will take this red path from A to B in this direction, and then I am taking in this direction. So, you see is here I am actually changing my direction according to my convenience, that is in this one I am taking this positive direction, in this I am taking the negative direction. Why? Because I want to keep the direction same direction for one path, That is why I am making it, and we do know that this Cauchy theorem is holding true whether we are taking is the direction is immaterial when the function is analytic on this simple closed contour. So, here I am taking this first this direction, and then C2 is this one. Similarly, for B to C I am taking again the positive direction, that is from C31 is this red one and C32 is this green one in this direction. Then C41 is your this red one in the negative direction now you see, and then C42 is green path from this direction. Since the complete sum has to be 0, so what it says is from here what I would get it actually that C11, now I am writing it in the two different manner. Now, I would break up the red path and the green path. Red path I would keep on the left side and the green path on the right side. Red path you see all the second indices as 1, that is what is our red path, and all the second indices 2, that is our green path. So, C11 this one plus C21, you do see is that is how we have taken C21, we have taken this path connecting from A to B. So, C11, C21, C31, C41, the path from Z1 to Z2, this path. This would be same as, now if I take C12, C12 is this path. So, minus of C12 means the path from Z1 to A. Then C22, C22 is the same path. C22 was we have taken is that the second one we have taken in this orientation. So, C22 was actually from from B to A. So, now minus C22 would be again from A to B. Then we do get from this side and minus of C32, then minus of C42, this one. So, what we are getting is actually you can rewrite it by your manner and see it clearly. We would be getting that the integral along this path would be same as integral along this path. So, whatever be the path, if the function is analytic in this whole domain D, which is simply connected, then for any analytic function the integral is independent of path. If it is independent of path, then in last lectures we had seen is if indefinite integral does exist, or that is also we are calling is antiderivative, we could write the integral very easily, that is we do not have to see from which path and we do not have to find out the function along this path, or we do not have to write the parametric equation of the path. We just have to know the points Z1 and Z2 and the function and its antiderivative, and that way we can write the integral value. What does this Cauchy theorem also makes that antiderivative exists? You see, the Cauchy theorem also says is that we can use the Cauchy theorem to say that antiderivative exists. You see, one more thing in between, we are talking about principle of deformation of path. As we are saying is it is independent of path. So, if the function is analytic on every path here, whatever the paths I have talked about from C1 to C2, these are 2 points we are talking about, and keeping these fixed ends, if we just take any path, you see is that is we are changing our paths in this one. This is one example you could say is you can make it any other manner. Integral of any analytic function, when the function is analytic on these paths and its interiors, or rather you could say only on the paths, we do find out that these integrals will remain same. This is called actually the principle of deformation of path, that is we can deform the path from C1 to C2. So, just I am writing this thing, path C2 is obtainable from C1 by continuously moving with fixed ends. Hence, for analytic f, value of integral does not change. This is called the principle of deformation of path. So, now come to this existence of indefinite integral. If a function f is analytic in a simply connected domain D, then there exists an indefinite integral capital F z of a small f z, which is analytic in D, and for all points in D, joining any two points z0 and z1 in D, the integral is independent of path and can be given as integral from z0 to z1. Now, you see I am not writing it that is integral along the path C, I am just writing from z0 to z1 of fz dz is as capital F of z1 minus capital F of z2. You see, we had proved the Cauchy theorem when we had assumed that derivative of f was continuous. As I told you that f dash, the continuity of f dash was not required, that the proof was given by Gaussian, but that I have not done here because it is little bit more involved. So, you see now we are moving towards, that is when this f z is only analytic, we are not talking about any condition on the f dash being continuous, but what we have added up, that is we have added up the condition that it is a simply connected domain. So, here what we are saying is, of course, we do know along any closed contour the integral is 0. From there we had obtained that it is independence of path. So, these points we have got, that is because f is analytic in the simply connected domain. Then any path, if z0 to z1 I do take a closed contour, we do get is that the integral along to that would be 0, that gives us independence of path. Now, the thing here what we are saying is that indefinite integral capital F z of f z is existing. This capital F z sometimes also we call antiderivative. So, let us see the proof of this theorem, how we are going to do. Let us have these 2 points, that is a fixed point z0, and I am having any path in that domain D from z0, it is moving one to z. So, be this one, and I define now capital F z. This is being defined as integral from z0 to z f s ds along this path. This path is in that domain D. Now, we want to show that this function is actually existing. This function will exist because this is a path in simply connected domain D. Its integral along any path from z0 to z, either I take this path or that path, it will always be same. That says is, since the value for each one would be same, so existence you could say is, from here we are just saying is that this does exist. So, I have defined that this is existing. Now, the thing which we want to say is, that is this is actually antiderivative of f, that is if I do not take these limits, I should say capital F z is integral of small f z dz. For that what we will do is, we will take this function f z and we will show that the derivative of this function capital F z is a small f z. That for that we will use the first definition of derivative. So, for that what we will take? We will take one point z plus delta z in the neighborhood of z, and will extend this path, a straight line we could say, till this one. Now, this I have taken in a small neighborhood of z. So, it is again inside our domain, and the function is analytic, because function is analytic in whole domain. So, we are saying is the function is analytic in that path, on that path, extended path also. So, if it is happening, then according to this definition, how we have defined this capital F z, I could write this capital F z plus delta z as integral from z0 to z plus delta z of f s ds. Now, for using the first definition, I want the difference of f z plus delta z with f z. What will be that difference? By this definition, it would be simply integral z0 to z plus delta z f s ds minus integral z0 to z f s ds. That is integral from here to here minus integral from here to here. We do know from this contour integration that this would be nothing but the integral of f s, that function f, on this small path from z to delta z. So, that is what we are writing is, it is nothing but z to z plus delta z f s ds, and if I am dividing it by delta z, so I should have this 1 upon delta z outside. Now, what we have to show, that this limit of this is a small f z. How do we go? Again we will go with the first definition, that is I will take its difference with small f z and show that this difference can be made arbitrarily small when delta z is made arbitrarily small, or when delta z is this z plus delta z is approaching to z, or this delta z is approaching to 0, the difference of this function with small f z can be made very smaller, that can also approach to 0. So, let us try for that one. Let us first see from z to delta z, z plus delta z, this length of this path is only delta z. So, now write this the length of path formula, we do get delta z is integral of z plus delta z ds. That says is, now if I take f of z, that is at this point, that is independent of all the points which are inside this on this simple line from z to delta z. So, from here what we could write, f of z I can write as 1 upon delta z integral z plus delta z f z ds. Why? This f z is independent of any points, that is it's not integrable over here. This integral is this f z is constant with respect to the all the path of integration, that can be taken out, and this integral would be nothing but delta z. So, delta z upon delta z is 1. So, this is f z, that we could write. Now, come to this f z plus delta z minus f z upon delta z minus f z. You see, both I am getting is 1 upon delta z is common over both, and in both the things I am having the integral from z to z plus delta z. Of course, here is the function f s and here is the function f z. Again with the using the properties of this contour integration, you could say we could rewrite it as the same integral from z to delta z, and we would write f s minus f z. So, let us see that is how we are writing it. We are writing it as f z plus delta z minus f z upon delta z minus f z as 1 upon delta z, z integral z to z plus delta z of f s minus f z ds. Now, you see, we want to make it arbitrarily small. So, we take the modulus of this one, modulus of this one would be modulus of this one. With the modulus property, we could write 1 upon mod of delta z and then mod of integral absolute value of the integral z to z plus delta z f s minus f z ds. Now, for finding out the absolute value of this one, what we actually we have to show that this is arbitrarily small. So, for this now what we will do, we will use this ML inequality, if you do remember. Now, you see f s minus f z, what is my reason of integration? Z to z plus delta z, and we are talking about this path. So, what we are talking about in this path, you see any s over here, its difference with z, that will always be less than delta z. Since I am taking a small neighborhood, so let us take this delta z is small enough. Since f is analytic, so this small f is analytic. So, f would be continuous in this domain. By the definition of continuity, if I am taking any small neighborhood of the z, then the difference between the 2 points is small. That says is that the f s minus f z would also be small. Let us say this is epsilon. So, what we are saying is that f s minus f z mod of this would be less than epsilon. 1 upon delta z is as such, this is less than epsilon, and then the length of path is delta z. So, using this ML inequality, I am getting is this is less than epsilon. How we have done? I am just rewriting it. Since f s minus f z would be less than epsilon, whenever we are having is z, that s is in the small neighborhood of z because of the continuity of f. What it says is that now this I have taken in this path direction, this path. Now, because I said is that is I am taking z plus delta z as in the neighborhood. So, it is not necessary that I do take only this way, I can take here also, I can take here also. till it is inside that domain D, that simply connected domain D. So, whatever be side we could take it. Here I am just using this condition, whatever direction I do take this z plus delta z, all the times the path I would be having is that straight line over there, and it would be always, the independence of path says is that it will always be all the definitions of f z plus delta z and f z will remain same, and we will always get, because of the continuity of a small f, that this thing would be holding true. That says is this would be, can be made, this difference can be made arbitrarily small for any delta z, that is in whole neighborhood of z. What it says is, now use the first definition of the derivative. It says is that limit as delta z approaches to 0 of f z plus delta z minus f z upon delta z would be small f z. What does it says? It simply says, by the definition of derivative, that the derivative of capital F z is small f z, or in other words we write that capital F z is nothing but the antiderivative of small f z. So, we have got z is also arbitrary. So, we have got that and the z also we have taken the arbitrary. So, now we have got this capital F z is analytic in whole of the domain D, and its antiderivative is and is the antiderivative of small f z, that is we could say f z is integral f z d z. Now, you are saying is that is I am not taking it z naught to z. Now, what we are saying is that since my z I have taken arbitrary, the z naught also I have taken arbitrary point. So, now I can use it in general and I can write this antiderivative does exist. Antiderivative does exist, that says is my function capital F is analytic in that whole domain D. Now, if it is happening, and suppose there is another, suppose there is some other antiderivative of this small f which is capital G z, then what will happen? We would say is, because G z is antiderivative, that means G dash z will also be small f z. So, the difference of G dash and f dash, that would be small f z minus small f z, that will always be 0 for all z. If I, because they are antiderivatives and this they are the derivatives of f and capital F and capital G, if I integrate it, we do know that G z minus f z should be a constant. Now, here because we are talking about the complex one, so this should be a complex constant. What we say, if there does exist any other antiderivative capital G of a small f, that would be nothing but addition of a complex, the difference of these two would be nothing but a complex constant. That says is what will happen, the output of the our theorem which said is that integral along from z naught to z 1 of f z d z, that is f of z 1 minus f of z 2. Now, you see, if why I am talking about this one, if capital G is some other antiderivative, then what it will happen, it will be actually capital G of z 1 minus capital G of z 2. So, how do I say is this should capital F of z 1 minus capital F of z not only? You see, what is capital G z? Capital G z would be nothing but f z plus a. So, G of z 1 minus G of z 2, when z naught whenever I am writing, I would again write substitute it as f z plus a, because a is a fixed constant. So, whether we are changing is z naught or z 1, that does not make change in the a, I will always get this one. That says this, the antiderivative is existing and the definite integral, or that integral between the 2 points z naught and z 1 in that simply connected domain of this small f z, can be given as capital F of z 1 minus capital F of z naught, where capital F z we are defining as the antiderivative of small f z without a complex constant. So, thus we have got Cauchy theorem says is, if my f is analytic in a simply connected domain D, then its antiderivative does exist and the integral is independent of path, and then we can use this simple formula. That says is, now explains our example which we have done in the last lecture. So, let us do one example. evaluate the integral z square dz from 0 to 1 plus I. You to see that this we have done the example in the last lecture and we had done it along some paths. Here we do know that z square, this function is actually entire function. So, whatever, because this is an entire function, so whatever domain I am taking where this 0 and 1 plus I is lying, this f z would always be analytic. So, and the antiderivative of this z square we do know is z cube by 3, that you have done in some simple some lectures on this derivatives of this one. So, if I take the derivative of z cube by 3, it would be actually z square. So, according to this result which we had find it out, integral from 0 to 1 plus I z square dz should be z cube by 3 integral from the evaluation from 0 to 1 plus I, that says is 1 plus I cube by 3 or it is 2 by 3 minus 1 plus I. You can compare this result which we have done in the last lecture. Similarly, if I do take the function e to the power z or any integral power of z or any other analytic function, any other entire function, then the derivative of antiderivative of all those functions we do know, because in the differential equation derivatives chapters you have done the derivatives of these functions, and since they are entire functions, so whatever the 2 points we are taking we can write it out, but it is not necessary that we do talk about only entire functions. Of course, for entire functions we do not have to see any other thing, that is for entire functions we will not see where the points of integrations have been given or whether they are lying, the function is inside that one is in a simply connected domain or not. For entire functions we do not have to see those things, but it is not necessary that we do apply it only the entire function. We could have analytic function in some domain. If that domain is simply connected and the points are inside that domain, still this theorem is applicable. So, today we had learned that when the function is analytic in any domain, then its integral is independent of path. Moreover, we had learned that its derivative is existing and its antiderivative is existing, or we called it indefinite integral, and then the integration can be find out using that antiderivative or indefinite integral evaluated at that the points, or that is the limits. And this is very simple as we have done in the definite integrals in the real analysis. So, we have come across the similar result as in the real analysis for the complex functions in the complex domains also. So, very nice result. That is all for this today's lecture. We will move little bit more from here, that if function is not analytic, it is analytic everywhere, but at some points it is not analytic in the domain, but it is analytic on the path, what will happen and all those things. We will discuss little more about this one. Till here we had come to that its complex analysis or integration of the complex function is similar to that of the real integrals or whatever we have done in the first course in the analysis. So, that is all for today's lecture. Thank you.